Hello learners, I hope you all are doing well and all set for the new normal mode of teaching that flourished in the time of COVID-19 pandemic. Myself, Dr. Swati Gupta, and I work as an assistant professor in the Department of Chemistry, Bhaskaracharya College of Applied Sciences, University of Delhi. Today we will be discussing about the basics of NMR, that is Nuclear Magnetic Resonance Spectroscopy. Hope you all like the video. Put your queries or suggestions in the comment box. So here we go. Well, to understand nuclear magnetic resonance spectroscopy, we have to look into the properties of the nucleus which can impact its magnetic behavior. One such property is nuclear spin. Many atomic nuclei behave as if they spin on an axis of rotation, just like Earth rotates upon its axis, which bring about day and night. Although we don't know whether nucleus actually spins or not, this nuclear spin is just like the spin property of an electron, which can have two spins, plus half and minus half. They have quantized spin angular momentum and magnetic momentum, and magnetic moment. The total angular momentum depends on its spin, or rather we would like to say on its spin number I. Interestingly, this spin number can be calculated using nuclear shell model. And most of the books say that we can't calculate, but we can actually calculate it using nuclear shell model. This is nuclear shell model, where there are different quantum energy states which split due to spin orbit effect. Just like electrons, nucleons, that is total number of neutrons and protons, fill these states according to the multiplicity of each state. So protons and neutrons tend to pair up, so that the spin of each pair is 0. So we have three cases. First one is when both number of neutrons and number of protons is even. So in case of even nuclides, both atomic mass and atomic number are even. So they have 0 intrinsic spin. When the atomic mass is odd, that means either there is one unpaired neutron or there is one unpaired proton. In that case, the spin of the nucleus is equal to the J value of that particular unpaired nucleon. The J value is, like in this case, if we have 1d 1 by 2, then 1 by 2 will be the J value. In third one is when we have odd nuclei. In that case, the total angular momentum will be the vector sum of angular momentum of individually unpaired neutron and proton. So,
Now, the observed spins can be rationalized on the basis of atomic number, that is the number of protons, and mass number, that is the number of neutrons and protons together. So let us take the first case when mass number is odd and the atomic number is either odd or even. Then the spin number will come out to be half integer, 1 by 2, 3 by 2 or 5 by 2. So, depending upon this, the number of spin states could be calculated from the formula 2i plus 1. So, for the half spin number, the number of spin states comes out to be 2. For 3 by 2 spin number, the number of spin states comes out to be 4. And for 5 by 2 spin number, the number of spin states comes out to be 6. And the examples for these are proton, carbon, nitrogen, fluorine, etc. Now let us take the second case when mass number is even and also the atomic number is even. In this case, the spin number comes out to be 0 when you calculate. Which means there is no spin for such nuclei. And the number of spin states for such nuclei calculated using formula 2i plus 1 comes out to be 1 only. And the examples that fall under this category are carbon, oxygen, sulfur in both atomic number states 32 and 34. Now the third case is when mass number is even and the atomic number is odd. The spin number comes out to be complete integer, either 1 or 3, and the corresponding number of spin states calculated using 2i plus 1 formula comes out to be 3 and 7 respectively. And the examples that fall under this category are deuterium, nitrogen and boron correspondingly. So what in a nutshell we can say, elements with either odd mass or odd atomic number have the property of nuclear spin.
Let's get to our next section, proton nuclear magnetic resonance spectroscopy. Although there are many nuclei which show the nuclear spin or which behave as tiny magnets, proton and carbon 13 are the most important nuclear spins to organic chemists.
So let's begin with proton magnetic resonance. The circulation of a charge generates an electric current which is associated with a magnetic field. It happens because the nuclei are positively charged. The spinning nuclei generates a magnetic moment vector known as mu. There is an axis of rotation passing through the center of the nuclei, which is also known as the nuclear axis. In protons, the two states are equivalent in energy in the absence of a magnetic or an electric field. The protons are also rotating around the nuclear axis, and these two states are equivalent in energy. They can rotate either clockwise or anti-clockwise, and thus the value designated for these spin energy states is either plus half for clockwise direction or alpha, and minus half 1 by 2 for anti-clockwise direction or beta. These nuclear spins are oriented randomly in the absence of an external magnetic field. They go here and there like we have gaseous molecules free in a space. They move randomly, occupying the total space. Similarly, these nuclear spins are oriented randomly in the absence of any external magnetic field. That external field beta naught. But when the field is applied, the nuclear spins get in specific orientation. Some are aligned parallel to the field, some are aligned anti-parallel to the spin. Now those which are aligned parallel to the external field applied, they are lower energy orientations and they are more likely to happen. That means more the number of spins are going to be aligned parallel to the external field applied. Now the other nuclear spins that are aligned anti-parallel to the external field happens to be those of higher energy orientation and they occur less likely. So the two spins alignments parallel and anti-parallel are attained on application of external magnetic field.
Please subscribe my channels for notification about my latest videos. Hope you liked the video. Thank you.